Hello, welcome back. We're going to tackle an age old question today: 1D or 3D? Is 1D good enough? Do I need 3D? So that's what we're going to talk about. Before we go to a couple of examples, just look at the difference, the fundamental difference between a 1D scanning LDV and a 3D scanning LDV. So 1D, and remember, it's all sequential scanning. 1D, there's one sensor head. The scan happens on a predefined grid that you can define, of course, and the beam is sequentially scanned along the predefined points. You have one scan head with a pair of mirrors that are accurately controlled to go to those locations. So here what you're getting is what we call out of plane. So just the direction of the laser beam, or sort of normal to the surface. That's the component you are getting. As compared to that, now let's look at a 3D. So yeah, 3 times the number of scan heads. So now we have 3 scan heads. But again, the fundamental concept remains the same, sequential scanning. But now using all kinds of software and image processing and coordinate transformation, we are sequentially scanning at all those points. But in 3D, where you have 3 beams extremely accurately superimposed at the predefined locations. Now, in this case, instead of just getting the out of plane or Z, you are getting out of plane and 2 in plane directions as well. So when we look at the fundamentals of it, these are guidelines, not rules or laws, So 1D is usually preferred for simpler structures, panels, or structures where most of the action is happening out of plane, in the Z direction, right? Uniaxial motion, so flat panel vibrations. If you're into, boundary element or, acoustic analysis, then mostly you're interested in surface normal velocities. So there it's okay, you can use it. Or if you're just into simple ODS, operation deflection shapes, you just want to see what's happening. You're not getting into any correlation work. So all those cases, 1D scanning is fine. Now, 3D is where you really have complex structures. Think of, complex geometries, even metamaterials where everything is so complex. Or if you're into wave propagation, FE model update is another one where you have the FE model is always going to be in 3D. So ideally, you would want to measure in 3D, right? Similarly, for strain work. Now, strain is a purely in-plane phenomenon. So you want to be able to measure it. Or there are some other cases like brake squeal measurements that's happening because of the cross-coupling between the out-of-plane and in-plane. There you want to measure in true 3D. Non-destructive testing or evaluation is another one where you may be studying wave propagation for defect detection. So these are think of more complex structures, FE model update, all those stuff are kind of ideal for a 3D measurement. Now, let's look at 2 examples, and I think that'll clarify, some concepts here. So let's go here, and we are going to look at, on the right, we have a 1D scanning LDV measurement. On the left, we have a 3D scanning LDV. So here, let me just play this and then play this as well. And you can see that on the right side, the motion is mainly out of plane, so you can easily use just a 1D and you can see the motion. Even when you go to higher frequencies, let's say about 6 kilohertz, still a lot of motion is happening out of plane. So this is okay. But now let's look at the one on the right side here. Here, it's just next to impossible to capture this with a 1D scanning vibrometer where you have this multimodal, multi-degree of freedom type response in various directions. Let's even look at some higher order frequency. Now you can start seeing that, trying to capture this with 1D would be a nightmare, if not, impossible. So these are the 2 cases that sort of, simple geometry, 1D is fine. Complex geometry, you really want to get to a 3D type measurement. I hope this helps clarify the difference between a 1D when it's good enough and when you actually want to do a 3D measurement. Thank you very much for your time. Feel free to reach out. If you're not sure, let's talk. We'll get to the bottom of it. Thank you.